All right, welcome to the Explainer. Today, we're going to crack a chemical case that's all about making the invisible, well, visible. And why does this matter? It's actually critical for all sorts of things, from checking the quality of our food to making sure our drinking water is safe. Knowing exactly what's what in a substance is a pretty big deal. So, picture this. I hand you a sample of salt dissolved in water. It's perfectly clear. Your mission, should you choose to accept it, is to find the exact amount of magnesium hidden inside. I mean, how do you even begin to measure something you literally cannot see? Well, it turns out chemistry has this just beautifully elegant solution. To pull this off, we're going to need a very special tool. So let's meet the absolute star of our show, a molecule called EDTA. Okay, so the super technical name is ethylene diamino tetraacetic acid. Yeah, I know. It's what chemists call a chelating agent. But that's just a fancy way of saying it's a molecule that's basically designed to form these incredibly stable, super strong bonds with metal ions, like the very magnesium we're hunting for. Honestly, the best way to picture it is like this. EDTA is a chemical claw. When it bumps into a magnesium ion that's just floating around in our solution, it reaches out and just grabs it in this unbreakable grip. It is just unbelievably good at latching on. And this is the really crucial part. It's all about this perfect one-to-one ratio. For every single molecule of EDTA we add, it grabs exactly one ion of magnesium. Not two, not maybe 1.5, but exactly one. You gotta remember this, because this perfect ratio, it's the key to solving this entire mystery. Okay, so we've got our chemical claw, EDTA, ready to go out and grab all the magnesium. But wait, that brings up a whole new problem, doesn't it? I mean, how in the world do we know when the job is done? The solution is colorless, the magnesium is invisible, and the EDTA is invisible too. We need some kind of signal flare to tell us, hey, you've grabbed the very last magnesium ion. And that signal flare comes from another cool chemical, the calmagite indicator. This stuff is a special dye with a really neat trick up its sleeve. It tells us the exact moment our titration, which is just that process of carefully adding our EDTA, is complete by changing the color of the whole mixture. So here's the really clever part. Check this out. Before we get to the end, the calmagite indicator is actually holding on to some magnesium ions itself, and that makes the whole solution this really distinct wine red color. But here's the thing. EDTA's claw is way stronger than the indicator's grip. So once all the free-floating magnesium is gone, the very next drop of EDTA literally rips the last magnesium ion right off the indicator. And the second that happens, boom, the solution instantly flips to sky blue. That color change is our big flashing stop sign. Now, to pull this off with any kind of accuracy, we can't just go in and start splashing our chemical claw around. No way. We need a precise two-step mission. Our mission? It breaks down into two critical parts. First, we've got to standardize our tool to make sure our measurements are dead-on accurate. Then, and only then, can we use it to find the magnesium in our unknown sample. So, step one, standardization. Think about it this way. You wouldn't try to measure a room with a ruler if you didn't trust the markings on it, would you? Of course not. It's the same idea here. We react our EDTA solution with a substance we know everything about, a super precise standard of calcium carbonate. This lets us calculate the exact concentration, or the strength, of our EDTA solution. We're basically making sure our chemical claw is perfectly measured. All right, now for the main event, step 2, the determination. With our perfectly calibrated EDTA, we start adding it, drop by drop, into our unknown magnesium sample. It's got that calmagite indicator in there, so the whole thing is wine red, and we just watch and wait for that instant switch to sky blue. The key piece of evidence we're looking for is the exact volume of EDTA solution it took to make that happen. Okay, we've collected our evidence. Now it's time to put on our detective hats and interpret the data to crack this case. So it all boils down to that one crucial number we measured from our equipment. That number is the exact volume of EDTA it took to turn that solution from red to blue. And because we did that whole standardization step earlier, we know the precise concentration of that EDTA. So when we multiply the volume we used by that concentration, it tells us the exact number of EDTA molecules we added. In chemistry, we use this unit called a mole. which is really just a handy way to count a ginormous number of molecules all at once. And this is where it all just clicks into place. Remember that perfect 1-to-1 ratio we talked about? One chemical claw grabs exactly one magnesium ion? Well, that means if we used a certain number of EDTA molecules to get that color change, then there had to be that exact same number of magnesium ions in our sample. The number of claws we used is equal to the number of ions they grabbed. We found our invisible target. It's amazing. And once we know the moles of magnesium, it's just a little bit of straightforward chemistry math to figure out the final mass, and then the percentage of magnesium in that original salt. And just like that, case solved. So think about that. We started with something totally invisible, hidden away in a clear solution. And just by using a clever molecule and a simple color change, we made it visible, we made it measurable. It really makes you wonder, right? What other hidden truths are all around us, just waiting for the right chemical key to unlock them?